Hi, chemistry students. This is part 2 of our Introduction to Covalent Compounds and Covalent Bonding. And we're learning to use Lewis dot structures to draw structural formulas of simple covalent molecules. And we're going to be using that honk rule that I taught you in the previous video. I'm going to show you a couple of videos within this video that use the honk rule and the octet rule in order to write correct structural diagrams, structural formulas of simple covalent molecules. So the first one we're going to do, the simplest one, is CH4. So I'm going to show you the Science Geek video of how you can use both honk and octet and double checking yourself to be sure that you're doing these drawings correctly. So here's the first one.
Here we're going to determine the Lewis structure for methane, CH4. The first step in that process is to find out how many valence electrons the carbon and 4 hydrogens are contributing to the structure. So we go to our periodic table. We find carbon here, hydrogen here. Hydrogen's in the first column, so it has 1 valence electron. 1, 2, 3, 4. Carbon has 4 valence electrons. Return to the drawing. There's a single carbon, and it contributes 4 valence electrons.
Watch this process.
Hydrogen.
This is what you should do every time
there are
when you're drawing
4
these molecules.
hydrogens, each one contributing 1 valence electron. Gives us a total of 8 valence electrons in constructing this. To determine which atom goes at the center, we apply the honk rule. Hydrogen forms 1 bond, oxygen 2, nitrogen 3, and carbon 4. Carbon wants the most bonds, so carbon goes at the center. We place carbon central and 4 hydrogens symmetrically distributed around carbon. With the nonmetals, every element but hydrogen wants an octet. Hydrogen only wants 2 valence electrons. So we're going to join the central carbon to the hydrogens with the electron pairs representing covalent bonds. And in doing so, carbon is surrounded by an octet of valence electrons. Each hydrogen has 2 electrons. And if we choose to redraw this at this point, we can replace the shared electron pairs, the covalent bonds, with lines representing bonds. Some classes that's required, in others it's not. Both of these are valid structures for the compound methane.
Okay, so you can kind of see the process by which you should draw these structures. So we're going to do a few more examples, and I'm gonna work through one with you. You should probably be writing this down as we go along, and if you have the guided notes, you'll see there's kind of a 1 through 9 sort of steps to go through this. So steps to draw this small covalently bonded molecular compound, nitrogen trifluoride, as you will learn how to name. Number 1, you're going to determine the number of valence electrons for each atom, because that's the only kind of electrons that will be shared in covalent bonds. You're going to add together and find the total number of valence electrons. You're going to arrange the atoms in a skeleton, and the atoms that wants the most bonds, according to the honk rule, goes in the middle. And it kind of goes in that order, right? Hydrogen wants 1, oxygen 2, nitrogen 3, carbon 4. In terms of this NF3, nitrogen would go in the middle because it wants the most bonds. Then you join the atoms to fulfill honk by the number of bonds that they want. Again, 1 for hydrogen or the halogens, 2 for oxygen, 3 for nitrogen, and 4 for carbon. And you have to have that number of bonds. Then you're going to add the unshared pairs to follow the octet rule so that everybody has that full outer energy level. Then you're going to count the number of valence electrons and see if you need any double or triple bonds in order to fulfill the octet rule and to use up your valence electrons. Okay, so let's go ahead and think about this. You're going to determine the number of valence electrons in each atom. And for nitrogen, that would be 5, and in each one of the fluorines have 7. You'll add up the valence electrons, and so we have to have 26 electrons in our picture. The valence electrons must all be used, must all be shared, and no more or less can be in our proper structural formula. We're going to arrange the atoms in a skeleton. The atom that wants the most bonds is going to go in the middle. Then we'll join the atoms to fulfill the Honk rule and add any unshared pairs to follow the octet rule. And then we'll count everything up to be sure that everything is done. So again, we're going to arrange the atoms in a skeleton. We'll put nitrogen in the middle and fluorines around the outside. We know that nitrogen wants 3, fluorine only wants 1, according to Honk. So that's why nitrogen's in the middle. We're going to join them to fulfill the Honk rule. Now that could either be as a line or as 2 dots, okay? That's going to get rid of 6 electrons, okay? And we still have 20. What are we going to do with these other 20? Well, we need to add pairs to follow the octet rule, because right now, remember this line represents 2 electrons. So right now, this nitrogen only feels like it has 6. It needs to have a pair here, and each one of the fluorines only feels like it has 2. So it needs to have 3 unshared pairs around the outside. So we're going to do that. And excuse my weird thing here, but you can see we've got a pair here, a pair here, a pair here. We've got a pair on the nitrogen and so forth. So if we actually count all of these up, we end up with 26 electrons. Okay, so we don't need any double or triple bonds. So just to see this as sort of a little bit more clear, here is nitrogen trifluoride. It has 26 valence electrons. 5 from the nitrogen and 21 from the 3 fluorines, 26 total. We need to arrange the molecule so that the atom that makes the most bonds go in the middle, that's nitrogen according to Honk. And then we need to make those bonds. So the fluorines each have 1 bond, the nitrogen has 3, that's great. We have 6 electrons, you can see them here as dots, 6 electrons that are being shared. And then we have all these non-shared pairs, these non-bonding pairs that must be used to fulfill the Honk rule. Now if we count up all the electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, you see we have 26 valence electrons in the picture. So this structure is correct. Now we can replace these 2 shared electrons with a line, but we do have to maintain the unshared pairs in order to show that octet. Just remember that line means 2 shared electrons or 2 electrons. Okay, so if you want the structural formula as opposed to the dot diagram, you replace dots with lines. So if you're sharing 6, you'll have 3 lines. Sharing 2 pair or 4 will have 2 lines, or 1 pair or 1 shared pair or a single covalent bond will have 1 pair of dots or 1 line. And again, 3 lines is called a triple bond or 6 electrons. 2 lines or 4 electrons is called a double bond, and 1 line or 2 electrons is called a single bond. All right. So again, as he showed you in a previous video, the Honk structures with the correct number of bonds, you're going to end up always choosing from these. So if you have a carbon, it could either have 4 single bonds or 2 double and 2 single. It's always going to have 4 lines coming from it and no pairs that are unshared. Nitrogen, on the other hand, again, is going to have 3 bonds, but 1 lone pair. It's always going to have this, when you think about its dot structure, going to have this 1 pair that is not shared. So these are the 3 possible configurations that you would have for nitrogen in a molecule. And again, notice all the nitrogens have a pair and 3 lines in some fashion coming from them, 3 bonds, either 3 single, a double and a single, or a triple. Oxygen has 2 non-bonding pairs, unpaired electrons that can form bonds, and 2 pairs that are not in bonds, lone pairs. So it is going to need to find 2 things to share with or to have a double bond. Halogens like fluorine only need 1, so they're only ever going to bond. They're never going to be in the middle of a molecule because they can only make 1 bond. And of course, the noble gases, That's why they can't form bonds, because they have no electrons that are not already paired up. They have a full outer energy level. Okay, so I want to show you two more quick videos on making double and triple bonds. We're going to start with the double bond. How would you draw a molecule of CO2? And it will incorporate a double bond. You should copy this example down.
This time the subject is going to be carbon dioxide, CO2. Looking at the periodic table, we see that carbon is going to have 1, 2, 3, 4 valence electrons, and oxygen will have 1, 2, 3, 4, 5, 6 valence electrons. So we have a single carbon with 4 valence electrons. Oxygens, there are 2 of them, 6 valence electrons each. So we have 12 and 4. We have 16 valence electrons with which to build this molecule. Applying the honk rule, oxygen wants 2 bonds. Carbon wants 4, so carbon is going to be central in this molecule. We'll symmetrically distribute the oxygens on either side. And the first thing we do is we go ahead and join this with electron pairs. However, it should become apparent that since oxygen is only joined to the carbon, each oxygen is only joined to the carbon, and oxygen wants 2 covalent bonds, that this bond cannot be a single bond, but instead has to be 2 shared electron pairs or a double covalent bond, as is the case with the other oxygen-carbon bond. In doing this, carbon is now surrounded by 8 valence electrons and 4 covalent bonds. If I were to rewrite this at this point, it wouldn't be complete, but you could see more easily the 2 shared pairs are written as a double covalent bond, and carbon has 4 covalent bonds around it. Oxygen, however, each oxygen in this drawing at this point has only the 4 electrons around it, and so we have to add 2 unshared pairs to each oxygen in order to complete the Lewis structure. Those could also be placed here in this drawing. 1, 2, 1, 2, 1, 2, 1, 2. Now, knowing we had 16 electrons, let's go back and make sure that our numbers work out. We have 8 valence electrons here in the center. We have 2, 4 more for 12, 2 more, 4 more, gives us 16.
Okay, and again, this would be the proper structure for CO2 with the double bonds. Everybody has fulfilled honk, everyone has fulfilled octet. Let's look at just one more example. This one will be with a triple bond. And again, a triple bond is sharing 3 pairs or 6 electrons.
The molecule this time will be HCN, hydrogen cyanide. This time we have 3 different elements. We have hydrogen, carbon, and nitrogen. We have 1 atom of each. So we go to our periodic table to find out how many valence electrons we have available. Hydrogen is 1 valence electron. Falling across, 1, 2, 3, 4. Carbon has 4 valence electrons. Nitrogen next to it, 5 valence electrons. So hydrogen contributes 1 valence electron, carbon 4, and nitrogen 5. We have a total of 10 valence electrons to build this molecule. Following the honk rule, H-O-N-C, carbon wants 4 bonds, carbon will be central. So we distribute the hydrogen on one side, which side, it doesn't matter. The nitrogen on the other side. Now, keeping in mind again, this honk rule, very helpful. It doesn't work all the time, but it is helpful. Nitrogen generally will form 3 covalent bonds. Here we have nitrogen only joined to the central carbon. And we keep that in mind as we put our electrons in place. Hydrogen always bonds to the carbon with a single electron pair. So we've taken 2 away. We have 8 electrons remaining. Now, carbon would like to have, I hesitate saying like, but carbon normally forms 4 covalent bonds. And there's only 1 covalent bond here. Nitrogen forms 3 covalent bonds. That strongly suggests to us that what we need between the carbon and the nitrogen is 3 electron pairs, 3 shared pairs, or a triple covalent bond. That uses up 6 more electrons and leaves us with 2. Hydrogen has 2 electrons around it. Carbon has 8 electrons surrounding it, an octet. But the nitrogen at this point only has 6 valence electrons. The remaining 2 electrons are being placed as an unshared electron pair on the nitrogen. We can rewrite this now. Carbon, nitrogen, hydrogen, single covalent bond between the hydrogen and the carbon. 3 lines, a triple covalent bond between the carbon and the nitrogen. And 1 unshared electron pair on the nitrogen to complete our drawing of hydrogen cyanide.
Okay, so those are some good examples. We'll do plenty more practice and activity in class.